Okay, hi, I'm Kiran Gopinathan, PhD student at the National University of Singapore, and today I'm pleased to present our research titled Certifying Certainty and Uncertainty in Approximate Membership Query Structures. This research was actually recently published and presented a week ago at the CAV 2020 conference. Okay, so there's this rather nifty feature of many modern web browsers, and that is that when you click on a URL that is known to be malicious, the browser will show a little pop-up indicating that the URL is malicious and shouldn't necessarily be trusted. Now, this is a pretty invaluable feature. However, its implementation raises a couple of interesting questions. In particular, how exactly does a browser know that a URL is malicious? Because on one hand, trying to store the database of all known malicious URLs locally is something that is, for performance and space reasons, practically infeasible. Conversely, sending every URL you browse to an external service is something that most users would find a bit invasive. So browsers actually implement this by means of a rather interesting compromise. They use a data structure known as a Bloom filter to store a space-sufficient local approximation of the set of all known malicious URLs. Now, by querying this local approximate set, browsers will only send up a URL to the external service if it has a relatively high likelihood of actually being malicious, thereby minimizing the number of unnecessary infractions on user privacy. So this feature, which safeguards the privacy of millions and millions of users, depends on two key properties provided by the Bloom filter. The first property, a no false negatives result, essentially states that the Bloom filter will only return a negative result for a given URL if that URL is in fact honest or not malicious. In other words, the Bloom filter will always catch any malicious URL. The second property, a low false positives rate, essentially states that for any honest URL, the likelihood of the Bloom filter giving a positive result, i.e. that the URL is in the set of malicious URLs, is going to be relatively low, thereby minimizing the number of unnecessary infractions on user privacy. So this system works quite well, apart from one small problem, and that is that the widely cited expression for the false positive rate of a Bloom filter is in fact wrong, and in fact has been the subject of 30 years of mathematical contention. And so our research tackles this problem by producing the very first certified proof of the false positive rate of a Bloom filter, and also generalizes our proof strategies to apply to a wider class of probabilistic data structures. So in the rest of this talk, I'm going to give you an overview of this research. We'll start by looking at what exactly Bloom filters are and how exactly these kind of interesting properties can arise. Then we'll look at how we managed to encode Bloom filters in Coq and how we managed to prove these properties in Coq. Finally, we'll look at how we managed to generalize our proofs to apply to a wider class of probabilistic data structures. Okay, cool, let's start. So what exactly is a Bloom filter? Well, put simply, a Bloom filter is just a bit vector, a sort of sequence of bits, paired with a set of hash functions. Now, when you want to use this as a set to insert an item, you'd hash it over each one of the hash functions, and then treating these hash outputs as sort of indices into the bit vector, you'd raise the corresponding bits in your bit vector. Now, conversely, when you want to sort of do a query for an element, you'd once again hash the input over each one of the hash functions, and treating the hash outputs as indices into the bit vector, you'd check that all of the corresponding bits are raised. And if all of the bits are raised, then the value is said to be in the Bloom filter, and otherwise it's not in the Bloom filter. So these operations are actually fairly simple and easy to implement in programs. However, they're actually sufficient to ensure the no false negatives property. And intuitively, the reason for this is that when you insert an item, you raise a certain set of bits in the bit vector. And there are no operations that can ever sort of unset these bits. This means that every subsequent query for that item must return true. From another perspective, the only way you can get a negative result is if, in fact, you had never inserted that item before. Because if you had, then you would have raised the bits. So this is a kind of a nice result for negative results. However, things get slightly more interesting when we look at positive results, because there is a possibility of false positives. Now, to see why this may occur, suppose we insert an item X, and it happens to map to a certain set of bits. Now, at a later point, we may want to query for some other value, y. Now, depending on the choice of hash functions, there is a possibility that the set of bits that y maps to will be a subset of the bits that x maps to. And in this case, even though y is not in the Bloom filter, our query will return true. In other words, we'll get a false positive. Ideally, we'd like to characterize the sort of rate or frequency at which these kind of events may occur. However, this is going to be highly dependent on our choice of hash functions. And so this is kind of not a general way of analyzing this data structure. So the standard way of performing this analysis is to assume that each one of the hash functions are sort of drawn uniformly at random. And then once we make this assumption, we can reason about the thing called the false positive probability, or the false positive rate, which is the probability after inserting sort of n elements into the Bloom filter. When we query for an element that has not been inserted into the Bloom filter, we get a positive result. We get a false positive. So when Bloom originally published this data structure, he came up with a sort of analysis for deriving this expression. So Bloom suggests we begin our analysis by looking at a slightly simpler case. Suppose we just focus on one particular bit of the bit vector. Suppose B1. Now, when we want to insert an item, we take that input and we hash it over each one of the hash functions. So when we hash it over the first hash function, because the hash functions are sort of independent and uniformly randomly drawn, we can treat the hash output as random. And so we can reason about the probability that the hash output will hit our selected bit. And this is simply going to be 1 over the number of bits, 1 over m. So naturally, the probability that the hash output misses our selected bit is just going to be 1 minus 1 over m. And in fact, as the hash functions are sort of independent, this expression is going to be the same for each one of the k hash functions that we map our input over. And so the probability that all of the hash functions miss our selected bit is just going to be 1 minus 1 over m raised to the power of k. And the nice thing is that this independence, assuming that each of the items that we insert, each of the n items that we insert are actually sort of distinct, each of these hashes is essentially going to be an independent draw. And so the probability that all of these hash functions miss our selected bit is just going to be this expression raised to an additional factor of n. So this expression here is the probability that after inserting n elements, our selected bit is going to still remain unset. So inverting this probability, we get that the probability that after inserting n elements, our selected bit happens to be raised is just going to be 1 minus that expression. Now from here, Bloom reasons that when we get a false positive, we query for some element, and it just so happens that each one of the bits that our queried element maps to happens to be raised. Each one of the k bits, because each one of the k hash functions maps to a bit in the Bloom filter. And so, assuming that the bits are independent, Bloom reasons that the probability that we get a false positive is simply going to be the probability that a single bit is unset, or is set, raised to the power of k, the number of bits that are selected by hash functions. And so this is Bloom's bound as he published it in 1970. Here it is in his original paper. And shortly after it was published, the Bloom filter became sort of fairly popular data structure, and it was quickly became a sort of mainstay of many engineering applications. And it was picked up, and this bound was repeated in paper after paper after paper. Unfortunately, it turns out that this bound is in fact wrong. This was found by some subsequent researchers sort of 30 years later in 2008, who realized that actually Bloom's assumption that the bits were independent was not actually correct. And so based on this, they derived a sort of new expression for the false positive rate of a Bloom filter, which was technically correct. However, their analysis was actually incorrect. They made use of some incorrect definitions, and this was found sort of 2 years later. So clearly this field is in dire need of some sort of formal verification. And this was the primary impetus for us to start looking at how we might go about encoding Bloom filters in Coq. So our approach to encoding probability was fairly standard. We used a probability monad to encode random computations in Coq. This allowed us to construct arbitrarily complex random events by just composing simpler individual steps. And using this formalism, we were then able to actually encode hash functions as sort of random oracles. So here, hash functions take in an additional sort of state parameter. which tracks the set of all previously seen values. So if we call the hash function on a value we've seen before, then we get the same value as its initial invocation. And if we call the hash function on a value that we hadn't seen before, we get a sort of uniformly random output. Now, things get slightly more interesting when we moved on to encoding Bloom filters. And that is that when we started encoding Bloom filters, we made a rather interesting observation. And this observation was the fact that when we tried to encode Bloom filters in Coq, we found we could always decompose the implementation and the behaviors of a Bloom filter into modular, reusable subcomponents. In particular, by partitioning on whether we were dealing with the probabilistic or the deterministic component of a Bloom filter. So the probabilistic component of a Bloom filter would be the process wherein we take our input, we hash it over a sequence of hash functions, which are sort of random oracles, to get a sort of random sequence of outputs. The deterministic component is the process wherein we take these hash outputs, treat them as indices into the bit vector, and we raise the corresponding bits, or query them if we're doing a query. Now, the nice thing about this decomposition is that it quite closely follows our intuition for how these proofs go. So earlier, when I told you about the no false negatives property, I mentioned that the reason that it holds was because that when you insert an item, you raise a certain set of bits, and there are no way of ever unsetting these bits. And if you think about it, this property is essentially just a deterministic property. And so when we were trying to encode it in Coq, we were able to prove it by purely looking at the deterministic component of a Bloom filter. And this meant that our proofs could actually generalize to arbitrary choices of hash functions. So the no false negatives property holds irrespective of what type of hash functions you happen to use, or whatever properties they may have. So this is quite nice. And in this fashion, we were able to produce the very first certified proof of the false positive rate of the Bloom filter as being this expression here. It's slightly more complex than the one that Bloom originally came up with. The curly braces combinatorial operator at the side is a mathematical operator known as Stirling numbers of the second kind, which we also produced one of the first certified proofs for, which was a sort of rather nice offshoot of our research, because Stirling numbers sort of turn up in a lot of pure mathematical fields. So this is a nice little reusable fact that could be used in other future developments. So this was quite a nice result. However, it was quite a lot of work. And so we were kind of interested in working out whether we could actually generalize some of the insights, maybe some of the encodings, or maybe even some of the proofs to apply to other data structures. And when we started looking at other data structures in this area, we started noticing some rather interesting structural similarities between the data structures. So a particularly egregious example is the case of a counting Bloom filter. A counting Bloom filter has almost exactly the same structure as a Bloom filter, but rather than using bits, it uses counters. And this kind of structural similarity seems to hint to us the possibility of being able to reuse proofs between these two data structures. And in fact, zooming out from Bloom filters, we found that the structural similarities that we were looking at were actually common across a larger class of probabilistic data structures known as approximate membership query structures, which are a class of probabilistic data structures that all provide space-efficient encodings of approximate sets of objects, just like a Bloom filter. And so the natural question we had when approaching this was, can we verify this? And it turns out, yes, we can. So our decomposition that we'd found of sort of decomposing Bloom filters into deterministic and probabilistic components actually seems to be common across most AMQs we could find. And when we were able to perform this decomposition, we were very often able to achieve sort of massive proof reuse between these data structures, significantly reducing the burden of performing this certification. And finally, sometimes we were even able to get certain properties entirely for free, thereby reducing all of the burden. So just to give a sort of understanding of how this process works, we'll look at how we managed to go about formally verifying the properties of a counting Bloom filter. Okay, so a counting Bloom filter operationally is quite similar to a Bloom filter. When you want to insert an item, you hash it over each one of the hash functions, and then again treating the hash outputs as indices into the bit vector, into the sort of vector this time, rather than sort of raising the bits. This time, because each one of these elements is a counter, we increment each one of the counters. Now, similarly, when we want to perform a query, we take our input, we hash it over each one of the hash functions, and treating the hash outputs as indices into this vector. This time, rather than checking whether each one of the bits are raised, we check whether each one of the counters is greater than 0. So immediately you should be able to see some quite striking logical similarities between the implementation of a counting Bloom filter and a Bloom filter. And luckily, our proof strategy allows making use of this. So immediately when we start decomposing a counting Bloom filter into its probabilistic and deterministic components, notice that the probabilistic component of a counting Bloom filter, the process wherein we take our input, we hash it over a sequence of hash functions and get a sort of sequence of random outputs, is exactly the same as that of a Bloom filter. And so the nice thing here is that all of the proofs we'd proven about the probabilistic component for a Bloom filter could just be carried over, reusing all of those proofs. So this was a rather nice result. But wait, it gets even better. Because if you think about it, the deterministic component of a counting Bloom filter is actually quite structurally similar to that of a counting Bloom filter, or that of a normal Bloom filter. And intuitively, the reason for this is that when we query a counting Bloom filter, we don't look at sort of the full value of each one of the counters. We look at a rather simple binary property of each of the counters. We just look at whether they're greater than 0 or not. And so from this perspective, if you think about it, the behaviors of a counting Bloom filter are essentially just a superset of the behaviors of a Bloom filter. We still have a notion of whether a sort of bit or counter is raised, but this time we just happen to be tracking this sort of additional information about the number of times each counter was raised. And so exploiting this observation, our proof strategy allows carrying over all of the proofs from a Bloom filter to a counting Bloom filter by requiring us to just prove a rather simple deterministic reduction between the deterministic state of a Bloom filter and the deterministic state of a counting Bloom filter. And in this process, we were able to get all of those properties for free. And so this was rather nice. And so sort of building on these kind of ideas, we built this framework for verifying AMQs. We constructed these interfaces to represent sort of the abstract properties shared by AMQs and defined all of our proof strategies in terms of functors acting on these interfaces. So in this way, sort of for any new data structure, provided that they happen to fit to our interfaces, they can actually make use of all of our proof strategies to simplify their proofs. Additionally, we came up with a series of instantiations of these interfaces for a variety of commonly used AMQs, such as sort of Bloom filters, counting Bloom filters, quotient filters, and through this process we came up with a sort of zoo of AMQ components that could be sort of mixed and matched together to produce custom AMQs. A nice offshoot of this was that by mixing and matching these components in sort of novel ways, we were even able to construct entirely novel AMQs that had not been considered by the research before. But at the same time, they were actually correct by construction. So we elided the entire sort of controversy with Bloom. Okay, so that kind of wraps up the state of our framework as it is now. But for future work, there are a couple of directions that actually seem to show a lot of promise. The first idea is that currently our framework is tailored towards AMQs. But actually, we've looked at a couple of other probabilistic data structures, and we've noticed that there are actually there are structural similarities that we could still exploit. And so one potential direction for extending this framework is to try and extend it to apply to other types of probabilistic data structures, such as approximate counting structures, and sort of try and formalize the count-min sketch. Another interesting direction is that now that we have this very formal definition of the behaviors of a Bloom filter, there seems to be potential for trying to automatically infer sort of Bloom filter-based optimizations and insert Bloom filters to sort of automatically optimize programs. Okay, cool. So that concludes my talk. I hope you enjoyed. I'd be pleased to take any questions now. Thank you.